Welcome to The Explainer. Today, we're diving into magnetism. It's one of those fundamental forces of nature that was, for the longest time, a total mystery. It's this invisible power that's constantly shaping our world in ways we don't even think about.
So, where do we start? Well, it all kicks off with this really simple ancient puzzle. Think about it. How does a simple stone know which way is north? I mean, with perfect certainty. It's this one single question that baffled thinkers for centuries and, honestly, launched countless voyages of discovery.
Okay, so our story kicks off way back in the ancient world. And like a lot of great scientific discoveries, it starts with someone finding a weird kinda magic rock. A rock that would eventually change everything by leading to the first compass.
So this magic rock? Turns out it's what we call lodestone. It's basically a naturally magnetic piece of iron ore, first found at a place called Magnesia, hence the name magnetism, and people back then noticed something absolutely incredible. If you take a piece of this lodestone and just let it hang freely from a thread, it always, and I mean always, points in the same north-south direction. Can you imagine how mind-blowing that was? It was a total game changer. In fact, the Chinese figured this out way back, around 2500 BC, and used it to build the very first compasses. And just like that, navigation and exploration were changed forever.
So, playing around with these stones, people pretty quickly figured out the #1 rule of magnetism. You've probably heard this one. Every magnet has two ends, a north pole and a south pole. And the rule is simple. If you try to push two of the same poles together, like two norths, they repel. They literally push each other away. But if you bring opposite poles together, a north and a south, they snap together. It's this fundamental dance. Likes repel, opposites attract.
But okay, that's just the beginning. The story gets way more interesting. The real magic isn't just what a magnet is, it's what a magnet can do to other stuff. It can actually share its power. It can turn a regular old piece of metal into a temporary magnet. And this process, it's called induction.
So let's break that down. What is induced magnetism? It's just what happens when you bring a magnet close to something that can be magnetized, like, say, an iron nail. For that moment, the nail itself becomes a magnet. Pretty cool, right?
And this is a perfect way to see it in action. Okay, look on the left. You've got a plain iron bar, and it's doing nothing to those little iron filings. It's just a bar. But now look at the right. We bring a permanent magnet nearby, not even touching, and bam, all of a sudden that iron bar is magnetic, and it's picking up all the filings. But here's the kicker. The key word is temporary. The second you move that permanent magnet away, the iron bar goes back to being just a boring old bar. It loses its power. So what's the big takeaway here? It's this. When you see a magnet pick up a paperclip, it's not just a one-step thing. It's actually a two-step process. First, the magnet makes the paperclip magnetic. It induces magnetism. Then, and only then, the two magnets attract each other. So just remember this little phrase. Induction precedes attraction. It has to happen first.
Okay, this brings up a huge question, right? If this force can work across empty space, how? How does a magnet talk to an iron nail from a distance? To figure that out, we need a way to actually see this invisible force. And it turns out there's a really cool trick to do just that, to make the invisible visible. If you take a magnet, put a piece of paper over it, and then sprinkle iron filings on top, they don't just fall randomly. No way. They arrange themselves into these incredible, perfect, curved lines. You can see it right there. It's like we've suddenly got a map of this invisible power.
And that map, that whole area of influence around the magnet, that's what scientists call a magnetic field. Think of it like an invisible architecture of force that's all around the magnet. And those little iron filings, they're basically tracing out the blueprints for us, showing the field's shape, its direction, and even how strong it is.
Now these field lines have one very, very strict rule. It's unbreakable. They can never, ever cross each other. And why is that? Well, think about it. A compass needle can only point in one direction at any given spot. If the lines crossed, it would mean that at that single point the compass would have to point in two directions at the same time, and that's just impossible.
Okay, so we've got the basics down for these little bar magnets. Now let's scale things up. I mean, way up. Let's talk about the biggest magnet any of us will ever encounter, planet Earth itself.
You know, the whole reason a compass works, no matter where you are on the planet, is because the Earth acts like it has a gigantic bar magnet jammed right through its center. And this massive internal magnet creates an enormous magnetic field. It's like an invisible force shield that surrounds our entire planet and stretches way out into space. And how do we know this is true?
Well, we've got some pretty solid evidence. For one, as we already talked about, any magnet you hang up will point north-south. But check this out. This one is my favorite. If you take a plain iron rod and just bury it in the ground, pointing north-south for a while, the Earth's own magnetic field will slowly turn it into a magnet. How cool is that? And finally, as we'll see, you can find these weird neutral points where a small magnet's field and the Earth's field cancel each other out perfectly.
All right, get ready for a little mind bender. We all know that opposite poles attract, right? A north pole is attracted to a south pole. So, the tip of your compass needle that we call the north-seeking pole, it points to the Earth's geographic north pole. What does that mean? It means that our planet's geographic north pole is actually its magnetic south pole. It sounds weird, but when you think about it, it's the only way the physics works.
Okay, so this brings us to our final big idea. We know about the field from a small magnet. We know about the huge field from the Earth. So, what happens when those two fields meet? What happens when they overlap and interact with each other?
Well, you get these fascinating spots called neutral points. A neutral point is a place where the magnetic field from our little bar magnet is exactly as strong as the Earth's magnetic field, but it's pointing in the complete opposite direction. So what happens? They cancel each other out perfectly. The net magnetic force is zero. If you put a compass right there, the needle would just spin around totally lost because there's no north or south for it to find.
And here's where it gets really interesting. Where you find these neutral points depends completely on how you orient your magnet. So look at these two pictures. On the left, we've got the magnet's north pole pointing towards the Earth's geographic north. And see those little X's? Those are the neutral points, and they show up on the sides of the magnet. Now look at the picture on the right. All we did was flip the magnet around so its south pole is pointing north. And look, the neutral points have completely moved. Now they're on the top and bottom. This just proves that these invisible forces aren't random. They're interacting in a very specific, predictable, rule-based way.
So think about how far we've come. We started with a simple rock that somehow knew which way was north, and we ended up talking about a giant, invisible planetary shield that protects all of us from the sun's radiation. That's magnetism. It's this fundamental force that's all built on these beautiful, elegant rules. And it really makes you wonder, doesn't it? If we could figure out how to map this one invisible force, what other invisible forces are out there, what other hidden rules are shaping our entire world, just waiting for us to uncover them?